You're welcome back once again. LearnRite, our only business is to make you happy. It's to make you smile. It's to make you be able to learn your subject in a very easy way and understand it in a more and simple manner. So whatever we do, we illustrate with examples and prove how God created this earth or the universe for us all. Now today we are still on chemical bonding. We have talked about the two main types of chemical bonds that we have, the interatomic and the intermolecular. We discussed the various kinds of the interatomic bonds that we have, and we also listed the various types of intermolecular bonds that we have. We started with interatomic bonds. The first type of interatomic bond, we said it is ionic bonding. We have discussed the length and breadth of ionic bonding, going through all the 5 focal points in every bonding that we need to study. Remember, we said that the 5 focal points are the nature and the formation of that type of bond, the lattice occurring, the units occurring at the lattice sites, the intermolecular forces existing between the molecules of that type of bond, the examples of that type of bond, and of course the physical properties. So today, or in this video, we are going to look at metallic bonds as the second main type of interatomic bonds. As the name suggests, it means that we are going to discuss bonds that exist between the atoms of any metal. Remember, metals are more or less elements because they have only one type of atom in them. You can have 2 or more types of atoms in given metals, but anytime you have such a metal, it is called an alloy. That is a mixture of 2 different kinds of metals put together, and that in chemistry we call an alloy. Okay, an alloy. But here, this topic, we are going to discuss pure metals, the bonding that holds the atoms in pure metals together. So that's why I've written here nature and formation. Nature refers to what the bond is. So if I take these examples of bonds of metals, this is copper metal, an example of a metal within the transition series, very hard, compared to another type of metal within the group 1, 2, 3 series. Okay, this is an aluminum metal. It's a bit soft compared to the copper metal. With time, we understand why this is stronger. This is a stronger metal than that metal. If I brought magnesium metal, unfortunately we don't have magnesium metal here. Magnesium would also be softer than this aluminum metal. Magnesium would be let me say magnesium is softer, not would be. Magnesium is softer than aluminum metal. Very soon we'll explain why the strength of metals vary. But all I want you to know is that these are examples of metals. That thing we see here, this is an example of a metal. I think this is an aluminum metal as well, polished aluminum. And so, what is the type of bond that holds the atoms of a given metal together? Why is this a bit hard? It's all copper, 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 copper. In other words, copper bonded to copper, bonded to copper, bonded to copper. What is holding them together? That is what we seek to know. First here, I will explain and then I'll come back to define, so that when I define, then you understand what I mean by the definition. But what I've written here is something that I should have defined, that is the nature. But I want to do the formation. Then when I come back to define, you understand me. How are the bonds in metals formed? Now, let's see it. Copper metal, copper metal, copper metal. I've told you already in our previous video that bonding occurs within elements or molecules or atoms because they want to have their octet or duplet filled so that they'll be stable. But metallic atoms are such that they are just there, each other. They're not able to fulfill that stability that they want to achieve. That is duplet or octet. So what happens in metals is that the valence electrons in the metals themselves, the valence electrons will leave the atomose shell. And when the electrons, like I said, copper, 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 if you have this copper there, that copper there, that copper there, or if I decide to use lithium, 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 another one will be there. They are in that metallic structure together. What is happening to them? This lithium will have 2 electrons. 1 electron. This same thing will happen here. The same one with all of them. Then it will have 1 electron outside. So when the atoms exist there, they say, I have only 1 electron in my atmosphere. I cannot get a friend to bond with. I can't do anything. What they do is that the electrons in the atom's shell will leave. That one here will also leave. And that will come somewhere here. So this one will come here, this one will come here, and this will no more there. They will leave the atom's shell. And when they leave the atom's shell, then it means that the shell will no more exist. When the shell doesn't exist, the electrons, once they leave, they have created a positive center in here. Okay? They'll create a positive center in there. So maybe I'll come and get how did I get a positive center? Because the atomose electron, in the case of lithium for instance, it left the valence shell. This has become the inner shell. So that electron is hovering around here. Let me use negative so that we understand it. That electron so the electrons will leave the atomose shell and be outside the positive center of the metal. And when they see each other like that, once they have left, remember electrons are mobile. So they'll be moving. Then they'll merge into each other, into something we call an electron cloud. When they form that electron cloud, don't forget that the positive centers are also there. So then the positive centers, that's the positive metal centers, will try to also pull them together because now they are oppositely charged. And so the bond that holds the positive centers in place is due to the fact that the positive center is holding this electron that is hovering around it in the form of an electrostatic force of attraction, just like we studied in ionic bonding. So the positive centers are held in fixed positions, but the electrons are constantly moving around in that cloud. So when this electron, like this one, when this one moves this way, this one will move that way to come and replace it. So in between each positive position, you get an electron somewhere that doesn't allow the positive center to break down. It is held in position, just like a magnet, where you have a magnet here, and then that hard body magnetic substance is here. It holds it in position. When you move the metal, it will move in. When you move the magnet, to move in that substance. Try it in your laboratory, you see it. Okay, so the positive centers are held in position by a strong electrostatic force that is formed between the positive center and the free or delocalized mobile electrons. The electrons, when they leave the valence shell, all the positive centers will be formed because of the electrons leaving their valence shell. And so the two are held together by strong electrostatic force of attraction. And this is what holds every metal in place like this. We cannot see it with our naked eye, but if you use X-ray diffraction, you see it. Science, I told you, is interesting. You see it within this. that electrons are moving around, and there is that force of attraction holding the positive center at a fixed position. That is why that bond between the electron and the positive center being electrostatic makes the metal very hard. So if you say, what is the nature of metallic bond? You say metallic bonding is a force of attraction between the localized electrons and fixed positive metal ions. Metallic bonding, I'm now defining it. Metallic bonding is force of attraction. Some people will even use the electrostatic force of attraction to qualify it better. Metallic bonding is the electrostatic force of attraction between the localized electrons. The localized electrons means that the electrons are not fixed. Some people say they use the localized, free, or mobile. All of them are accepted. Delocalized. Delocalized means that first it was in a local position, now it has become delocalized. It's no more in a fixed position. Delocalized. Or free, or mobile. Any of them is accepted. So metallic bonding is an electrostatic force of attraction between mobile, free, or delocalized electrons and fixed positive metal ions or fixed positive metal centers. That is the definition. The formation is that you say that metals in a bid to fulfill its octet or duplet, the valence electrons move out of the valence shell and come together to form an electron cloud. That cloud then attracts the positive centers through an electrostatic force of attraction. The bond is established or becomes fixed. That is formation. So that is how metallic bonding is formed. So that is nature and formation of metallic bonding. B. Units of carrier and lattice site. Units of carrier and lattice site or lattice point. What will you see if you take an X-ray diffraction of that, of any metal? When you take any X-ray diffraction of a metal, you will see a positive center in a sea of the localized electron. If you take an X-ray, you will see that positive center with electrons around it. And again, you see positive center there. Okay? At the lattice site of every metal, what do you see? You don't see the lithium bonded with each other. No. You see the lithium plus with electrons around it. So if they gave you any metal, they said, what do you see at the lattice site of this metal? You say, you will see, take that metal, you see sodium plus immersed in a sea of mobile electrons. That's what you see. But if they make it general, what occurs at the lattice sites of metals, you say, at the lattice sites of metals, you see positive centers immersed in the localized electrons. But normally the question will come, giving you an example of the metal. What do you see at the lattice site of iron? You see iron plus. Okay, usually iron plus is +2, that's the stable one. You see +2 ions immersed in the sea of the localized electrons. That's all. C. What are the examples? Examples of metals. Many of them. Group 1, Group 2, Group 3 metals are all examples of metals. So from lithium to cesium, from beryllium to strontium down there, and then boron shows metallic characteristics, but sometimes it behaves like a non-metal. So we call it a metalloid. Substances that have those dual characteristics are called metalloid. Boron is a metalloid. Aluminum is a metal. An example I've shown here. If you come to all the transition metals, they are all metals. Okay? Right from the titaniums, the vanadiums, the nickel, iron, okay, cobalt, all of them are metals. First, second, third transition series are all metals. The gold and all of them, they are all metals. So if they ask you to write examples of metals, look at the periodic table. You can have countless of them, okay? We have 103, 104 substances. A number of them are metals. So those are the examples of metals. Now the next thing, that is the D. Intermolecular forces. Intermolecular. Look at it here. It's all atom, atom, atom. So if we take only one atom, which becomes 1 mole, the next atom is also 1 mole. So what do you think the intermolecular forces are? They are also electrostatic forces of attraction. They are also electrostatic force of attraction. So what is the intermolecular force in sodium? You say electrostatic force of attraction between delocalized electrons and positive sodium atoms. It's the same type of bond. So in ionic and metal, both the interatomic or the intra and the intermolecular are the same. Take note of that. Thank you so much. We will end here and continue to do the last thing, which is the physical properties. That I need to do a lot of illustrations. So we'll treat that in our next video. Come along. Thank you.